every bar magnet behaves as a magnetic dipole. So let ns be a bar magnet of length, let ns, n stands for north and s stands for south. Let ns be a bar magnet of length 2l and of pole strength qm. Suppose magnetic field is to be determined at a point P which lies on the axis of the magnet at a distance small r from its center as shown. Okay, so let ns be a bar magnet like this. South pole, north pole. And when we join south pole by north pole by this straight line, this line is called magnetic axis. This line is called magnetic axis. So we wish to calculate, now we wish to calculate the magnetic field at the axis of this magnetic dipole. We wish to calculate the magnetic field at the axis of this magnetic dipole. So a bar magnet is called a magnetic dipole. Now the length of this magnetic dipole, as in the case of electric dipole we used to take the length 2a, here we take the length as 2l. So this is the center of this magnetic dipole O. This is L. This length is also L. L, L, 2L. Now let us consider a point P. Let us consider a point P on the axis of this dipole, and the distance between the center and this point is small r. The distance between the center and this point P is small r. So the distance between this south pole and point P will be, this one is r and this one is L. So this is going to be r plus L. This is going to be r plus L. Again, the distance between north pole and this point P is r minus L. R minus L. Now, whenever we wish to calculate magnetic field at a point, then we always consider that a north pole is kept at that point. So suppose a north pole is kept at this point, then this north pole is going to repel that north pole. So Fn means force, a repulsive force exerted by this north pole at point P. Okay, so whenever we wish to calculate magnetic field at a point, we always consider that a north pole is kept at that point. So this north pole is going to repel this north pole. That's why this is Fn, means force exerted by this north pole. Now this south pole is going to attract this north pole. So Fs will be in the leftward direction. If you do not understand anything, please stop me in between. Imagine a unit north pole placed at point P, the same thing which I told you. Imagine a unit north pole placed at point P. Then from Coulomb's law, the force exerted by north pole of strength Qm or unit north pole will be, from Coulomb's law, Fn is equal to mu naught upon 4 pi Qm. Qm is, I am calculating this Fn. Qm is magnetic pole strength at point N. So this is Qm, and a unit north pole. Yeah, the unit north pole means magnetic pole strength at this point P will be 1. So Qm into 1 upon, what is the distance between N and P? It is r minus L. R minus L whole square. And what will be the direction? Direction is rightward. So along NP vector, along NP vector. This is equation number 1. Similarly, the force exerted by south pole. Similarly, the force exerted by south pole on unit north pole is Fs is equal to mu naught upon 4 pi Qm into 1. Now, the force exerted by this south pole on point P, though this south is going to attract it, this Fs. So, what is the force? It is Fs mu naught upon 4 pi. So, magnetic pole strength at point S is Qm, and a unit north pole is kept here. Unit means 1. So, magnetic pole strength of that unit north pole is 1. So, Qm into 1 upon, what is the distance between this S and P? The distance between S and P is R plus L. So it is going to be R plus L whole square. R plus L whole square, and direction along PS vector. Along PS vector. This is equation number 2. Therefore, strength of the magnetic field. Therefore, strength of the magnetic field B vector at point P is B axial at an axial point. B axial is equal to Fn minus Fs. Fn minus Fs. Why minus Fs? For calculating the net force of two different forces, it should be the addition of two forces. So Fn should be added in Fs. Yes, Fn should be added in Fs, but why I have taken this negative sign? Because Fn is in rightward direction, and Fs is in leftward direction. So Fn minus Fs, and let's put the values of Fn and Fs. It's mu naught upon 4 pi. It's mu naught upon 4 pi Qm upon R minus L whole square. Qm upon R minus L whole square minus mu naught upon 4 pi Qm upon R plus L whole square. Upon R plus L whole square. Okay, so we can take this Qm common. Mu naught Qm upon 4 pi. So this is 1 upon R minus L whole square minus 1 upon R plus L whole square. Minus 1 upon R plus L whole square. Now, take the LCM. So, while taking LCM, we will multiply both these terms. So, mu naught Qm upon 4 pi, mu naught Qm upon 4 pi, R plus L whole square, minus R minus L whole square upon R minus L whole square into R plus L whole square, mu naught Qm upon 4 pi R square plus L square plus 2RL minus, this is going to be R square plus L square minus 2RL, but there is a minus sign, so all the signs will get changed. Minus R square minus L square minus plus 2RL. Minus R square plus L square minus L square upon R minus L whole square into R plus L whole square. So this is R minus L into R plus L whole square mu naught Qm upon 4 pi 2RL plus 2RL is 4RL upon R minus L into R plus L is R square minus L squares whole square. Is this clear to you till now? Is this clear to you till now? Tell me.
Yes, sir.
Okay, but we know that magnetic dipole moment, m is equal to qm into 2l. Magnetic dipole moment m is equal to qm into 2l. M is equal to qm into 2l. Therefore, B axial is equal to, therefore, B axial is equal to mu naught upon 4 pi, mu naught upon 4 pi. Now we are going to take this qm inside, qm into 2l, qm into 2l into 2r, into 2r upon r square minus L squares whole square, r square minus L squares whole square. Now, for a short bar magnet, L is very less than R. It implies that R square minus L square is equivalent to R square. Because L is very less than R square, it means that uh, R square is very greater than L square. Okay, so R square is very greater than L square, so L square can be neglected. So we have neglected L square here, and that's why R square minus L square we have taken it to be approximately equal to R square only. Okay, then B axial is equal to mu naught upon 4 pi. What is this qm into 2l? It is m into 2r upon r square, because upon r squares whole power 2. And what will be the direction? Because we have taken this Fn to be positive and Fs to be negative. So what will be the direction? Direction will be along NP, rightward direction. It is along NP. Along NP, along NP vector. So B axial is equal to mu naught upon 4 pi m into 2r upon r squares whole square is r to the power 4 along NP vector r cube. B axial is equal to mu naught upon 4 pi into 2m vector upon r cube. This is the magnetic field at an axial point. This is the magnetic field at an axial point of a magnetic dipole. Is that clear? Anusha, is this clear till now?
Yes, sir.
Okay, and why I have dropped this one along NP vector, why I have written here 2m vector, it is because magnetic dipole moment, like electric dipole moment, was always from negative direction to the positive direction. The direction of electric dipole moment was always from negative to positive. In the same way, the magnetic dipole moment's direction is always from south pole to the north pole. So NP, what is this NP vector? NP vector, the direction of NP vector is from south to north. This is the direction south to north is the direction of magnetic dipole moment. So I have written 2m vector. 2m vector means it is automatically taking this direction along NP vector, this one. All right. Now, the next one is magnetic field of a bar magnet at an equatorial point. Shall I move on to the next slide? Anusha, shall I move on to the next slide?
Yes, sir.
Okay. Okay, wait for 1 minute. Magnetic field of a bar magnet at an equatorial point. Magnetic field of a bar magnet at an equatorial point. At an equatorial point. Now we are again considering the bar magnet. Now we have to calculate the magnetic field at an equatorial point. What is an equatorial point? An equatorial point lies on the perpendicular bisector. An equatorial point lies on the perpendicular bisector of any bar magnet. So now we have considered this bar magnet, and now we wish to calculate magnetic field at its perpendicular bisector. At its perpendicular bisector. Now, this is magnetic axis. This is south pole, and this one is north pole. And this one is point O. is L. From center to point P, we always take the distance to be R, small r, and take this angle to theta, this angle to theta. Okay. Now, again, let us consider this distance to be small x, and again, this distance will also be small x because these two triangles are contour triangles. This distance is n, this distance is n. Whenever we take the distance from any point on the particular bisector, those two lengths are same. Just ds and d are the same. So we have considered it as x. And what will be the value of x? X will be under r square plus l square, like other words. Now, whenever we wish to calculate magnetic field at any point P, then we consider a unit north pole to be kept at that point. So the north pole is kept at this north pole is going to return this north pole. Okay, so the direction of force due to this north pole is vector, and this south pole is going to attract this north pole. This is Fs vector. And vector, Fs vector. Now, let's draw this angle is theta. Let's draw a line parallel to these two lines, parallel to magnetic axis. So if this line is parallel to this line, this angle is theta. This angle is also going to be theta. Alternate interior angles. If this angle is if this angle is also theta, this angle is also going to be theta. Corresponding angles. Okay. Now, the resultant of both these forces will be in this direction. Consider the bar magnet as of length 12 and of close length Q. Suppose we wish to calculate magnetic field at a point P as shown. Imagine a unit north pole placed at point P, then from Coulomb's law, Fn is equal to Q1 upon 4 by Q1 upon x square along NP. Along NP, Fn is in this direction. So Fn is equal to Q1 upon 4 by Q1 into 1 upon x square along NP. This is the equation of the one. This is 1 upon 4 by Q1 into 1 x square along PS. Equation number 2. So that is in this direction along PS. So Q1 upon 4 by the charge, magnetic charge at this point. At this point is Q1. Similarly, at this point is also Q1. And magnetic charge at this point, we are considering the unit north pole that we have to Q1 into 1 along the distance of both of them is x square. Now, this is equation number 1 and equation number 2. As the magnitude of certain errors are equal, so the vertical components get cancelled by the horizontal components along here. So, the vertical components, magnitude of Fn and Fs, they are equal. Divided upon 4 by Q1 upon x square. Divided upon 4 by Q1 upon x square. Magnitudes are equal, so their vertical components, this one and this one, they both will cancel out each other. Okay, and horizontal component will be here. Fn cos theta plus this is going to be Fs cos theta. The Fs cos theta is also Fn cos theta because Fn and Fs are equal. So there, therefore, magnetic field at the equatorial point is equal. Equal means equal to the point. by u1 upon x square L upon x. L upon x. What is cos theta? Cos theta is base upon magnetism. L upon x. B equal is equal to u naught upon 4 by u1 into 2L upon x d is equal to u naught upon 4 by u1 into 2L is smaller magnetic dipole M upon x cube. What is x? X is under root r square plus L square. R square plus L square to the power 1 upon 2 and whole power is cube. Power to the power gets multiplied. Not upon 2 by now upon r square plus L square whole power is cube. For a short limit, for a short limit, that is very less than r. It implies r square. So it will be given L square. So L square can be negative. Means r square plus L square is approximately equal to r square. B equal is equal to u naught upon 4 by now upon what is r square plus L square? R square. The power divided by 2 will conservative. B equal u naught upon 4 by now upon r cube. Magnetic field that we put on the point of magnetic dipole is in the direction opposite to that of its magnetic dipole. That is from dot focus on. So we make V equal factor is equal to minus not upon 4 by 1 factor on r. Why is minus? Because this is in the opposite direction. The net direction, this is south and this is north. So direction of magnetic dipole is from south to north. So and this is in this direction. So this direction is north to south. North to south is opposite to that of south to north. That's why we have taken negative sign. Alright. Is that clear? Is this clear?
We are guidance. I'm not guidance.
Sure. What you going to keep us further? So we will take it. We will see tomorrow, and I will try if I get time. I can take your class in the first one if you are comfortable.
I'm there in the morning, the afternoon too. So if you have extra work or like, I don't know, questions or like the first part of the chapter, you can send them. I don't know. Or if you want me to write down a certain part, if you don't have write down the next one. So you can just teach and like finish.
You just learn the game. Just learn the game. There are some resources. So I consider that the class tomorrow and the day after tomorrow.
Wednesday, I don't know if I'll be able to have a class. Wednesday, I don't think we have a class. But Tuesday, we have class. And the weekend, I guess, yeah, weekend, it's for physics, I guess, next one is physics. So, full weekend, you have. So, you can give me extra questions for extra for even if you're not able to take the class.
Extra question is practice it from exam because it is having sufficient quantity of questions. So I will also give questions from there as well. So you can do by yourself all the questions are okay.
Okay, so.
Okay. Okay, Misha. We'll meet.
Mm-hmm.
Okay.
That is so awesome.